What is up, you guys? So in this one, we're going to talk about perturbation and sensitivity analysis. That is, for any classical optimization problem, we can introduce another optimization problem that is a perturbed version of this initial problem. We're going to see what it means to tighten or relax inequality constraints, and we're going to see how the optimal value of this perturbed problem reacts as a function of perturbation parameters, UI and VI. Not just that, we're going to introduce a global inequality that turns out to work also for any type of optimization problem given strong duality. That is, we're going to see how the optimal value of the perturbed problem reacts as a function of Lagrangian optimal pairs. We're going to see that indeed the optimal value of the perturbed problem highly depends on optimal Lagrangian pairs. However, this inequality is not symmetrical. That is, we know what happens in some cases that we're about to discuss. However, in the opposite cases, we don't know what happens. That is, let's say lambda star is large and minus u is positive. So we're pushing this lower bound upwards. So we know what happens to the upper bound. As a consequence, it is pushed upwards. However, we don't know what happens when lambda star is large and minus u is negative. The lower bound is pushed downwards, and thus we cannot say anything about p star of u and v. And that's why we're going to talk about local sensitivity analysis. That is, given that your optimal value of the problem is differentiable around its perturbation parameters u and v at certain points, and strong duality holds, we can see that the Lagrangian pairs are expressed as partial derivatives of the optimal value of the perturbed problem with respect to its perturbation parameters, and hence we have a symmetrical argument. We know what happens on both sides of the point, right? We're also going to give a shadow price interpretation in terms of economics as an example on local sensitivity analysis. So without further ado, let's get started. Okay, so let's say we've got the following classical optimization problem in front of us. That is problem P, where we're minimizing, as always, a certain cost f0 of x subject to some inequality constraints that are fi of x less than or equal to 0, and I've got m such constraints. Also, I've got p equality constraints, that is hi of x equal to 0 from I going from 1 till p. Now, say I'm interested in studying this problem upon perturbation. What do I mean by that? It means that we're still minimizing the same cost, but the feasible region is wiggled around its nominal position. So we're going to form another perturbed problem that is associated to this original problem, where we're going to see that upon strong duality, the dual variables not only help us in solving the problem, but also tell us important or give us useful information and insights about the sensitivity of the optimal value with respect to perturbations of its constraints. So now let's form an equivalent but perturbed problem. Okay, so I've changed the name of the first problem from P to C, C for classical, and the perturbed problem as P. As you can see, the only difference between problem C and P is that, instead of the 0 on the right hand side, so we've got UI and VI values, right? So notice that C and P coincide, so they're the same problem when all the UIs are equal to all the VIs are equal to 0. Okay. Now when UI is positive It means that we have relaxed the ith inequality constraint, right? Because it has more, space to wander around. It could be positive. If, let's say, UI is plus, I don't know, 2, it has more space to wiggle around, right? On the other hand, when UI is negative, we say that we have tightened the ith constraint. So when it's negative, it has less space to wander around. So if this is my, say, my real axis, this is my 0, right? So when UI is positive, as you can see, I've got more space. I have a wider range of feasible values, right? So in that case, we say that, I have relaxed my ith inequality constraint. However, when my UI is negative, I've got a tighter feasible region, right? So in that case, I say my ith inequality constraint is tightened. So I have tightened my ith inequality constraint. Now, problem P, the perturbed problem, results from C by either tightening or relaxing inequality constraints by a value of UI, right? And, just changing the right-hand side of the equality constraints with a value of VI, right? So, if you will, you're just adding a constant to HI of X. That's it. So if you get VI on the left-hand side, you've got HI of X minus VI is 0. This is like you're adding a slack to the ith equality constraint. That's all you're doing. Okay, you're not modifying variables of the problem. You're not adding x squared, x, a variable to the equality constraint. You're just either lifting or shifting down, depending on the value of VI, the ith equality constraint. Okay, now let's define a very important parameter. Let's define the optimal value of the perturbed problem. So as usual for C, our optimal value was always P star, right? So we always used to denote the optimal value of C by P star, right? So now, instead of P star, we're going to denote the optimal value of P by P star of U and V, right? Because it's a function of U and V. And this is to say that the more or less you perturb your problem, your P star will change. So having defined the optimal value of the perturbed problem, that is by definition, so let's write the definition down. It is the infimum, as always, of the original cost function, right? f0 of x, such that there exists x in the domain of the problem, right? Where you satisfy your constraints. That is, it belongs to the feasible region, or simply fi of x less than or equal to ui and hi of x is equal to vi. For all i's going from 1 to m for my fi, and for all i's going from 1 to p for my hi's, right? Now, without abuse of notation, U stands for, so U is a vector that contains all my UIs. So it contains U1 down to UM, right? Likewise, V is a vector containing all my VIs that are V1 down to VP, right? Okay. Now, some stuff to keep in mind here. It is possible to have a P star of U and V equal to infinity, right? So this guy could be infinity, which means that, as like in the original unperturbed problem, it means that the problem is infeasible, okay? So you don't have any point that belongs to the feasible region, right? So yeah, this is one thing to keep in mind. And another thing is that observe that P star, the particular value of P star evaluated at all 0 U and all 0 V. So P star of this particular value of 0, 0 is nothing other than P star, which is the optimal value of C, right? Because as mentioned before, when UIs are 0 and so are VIs, then the problem P is or coincides with problem C. Okay? Now, roughly speaking, P star is a function. So P star of U and V, if we go back here and write down P star and define it as a function, P star is a function that maps Rm by Rp towards R. Why Rm by Rp? Because U is of size M and V is of size P. So it's a mapping Rm by Rp that leads you towards R, right? And it gives the optimal value of the problem as a function of perturbations, right? So this P star is just reporting optimal values as a function of perturbations, U and V. When the original problem is convex, P star is also convex in U and V. And why is that? It's because the epigraph is nothing other than the closure of set A, where set A is the set that takes in the triplet U, V, and T, such that there exists an X in the domain where my Fi of X's are less than Ui for I going from 1 till M. My Hi of X equal to Vi for I going from 1 till P, and my F0 of X less than or equal to T. As you can see, this is the feasible region of the problem, P, in epigraph form. So in epigraph form, we mean that, as a revision, that this problem in epigraph form, let's say E of P, actually not E of P, let's say just E, yeah, E of P as such, not E sub P, okay, is that you're minimizing a scalar T, right, subject to the same constraints that is fi of x less than ui, hi of x equal to vi, and f0 of x less than t. So as you can see, the feasible region is now fi of x less than ui, that's 1, hi of x equal to vi, that's 2, and f0 of x less than t, that's 3, right? So this acts as the feasible region of the epigraph form of the perturbed problem, right? So what we were saying is that if the original problem P is convex, then P star has to be convex in U and V. You have to observe that the epigraph is precisely the closure of set A. Right, so now up till this point we defined the perturbed problem P of the classical 1C. We saw also that the optimal value of P could be seen as a function of U and V, right? So for every collection of perturbations, right, P star will change. Now, let's, the ideas up till this point seem really loose. So let's, try to find some inequalities that help us understand what's going on. And for that, we're going to, assume strong duality. So let's say for the moment that we've got strong duality, okay? What does strong duality mean? It means that P star is D star. P star is the optimal value of the primal problem, D star is the optimal value of the dual problem, okay? We talked about this in previous lectures. So let's say we've got strong duality and that the dual optimum is obtained. Know that this is the case if the original problem is convex and Slatter's condition is satisfied. Now let's denote, so P star is the optimal, we don't have to say this, but let's repeat it, it's okay to put all notations next to each other. So P star is the optimal value of C, problem C, and P star of UV is the optimal value, right? It's the optimal value of the perturbed problem P, right? What else do we need right now? We also have the duals, right? So we're going to define lambda star and nu star. So I'll just write it over here. Lambda star and nu star are optimal duals. That is, they're optimal for the dual problem of problem C, of the unperturbed or the classical problem. Then we can say that we have the following. So if I scroll down a bit over here, some space over here, yes, we can say that we have the following inequality. So P star of U and V is the upper bound or upper bounds the following. So P star or P star at 0, 0 minus lambda star transpose U minus nu star transpose V. Okay? Now, to prove this, it's really easy. All you have to do is pick a feasible point for the perturbed problem. So let's do that. Pick x in not A, but we really don't need to redefine the feasible region over here. But let's say X is feasible for problem P, then all what needs to be written down is that Fi of X is less than or equal to Ui for I going from 1 till m, and Hi of X is Vi for I going from 1 till P, right? And since we have strong duality, then we can say that so I'm just going to write down here strong duality, so plus strong duality, we can go ahead and say that P star at 0, 0, which is nothing other than the dual at lambda star and nu star, that's by definition of strong duality. So the optimal value of the primal is equal to the optimal value of the dual. This is D star, by the way. Well, now using the definition of the dual function g, that is the infimum of the following: f0 of x plus a sum on lambda I star fi of x plus a sum, well, let's write the limits. The first one is I going from 1 till m, and the second one is I going from 1 till p, going from nu I star hi of x, right? Well, the definition of g is that it is the infimum of this thing, right, of this quantity, except that it is not evaluated at the lambda star and nu star. Well, since it's the infimum, that it is always upper bounded by this quantity, right? Now, the second thing we're going to do here is that we're also going to upper bound this guy using ui and vi. So we know that fi of x is upper bounded by ui, right? And that hi of x is vi. So this whole thing will be upper bounded by lambda I star ui, right? Plus nu I star vi, right? Well, you can express this differently as, or in terms of vectors. So if lambda is my vector containing all the lambda i's, then I'll get a lambda star transpose u, okay? And likewise here I'll get a nu star transpose, where nu contains or is the vector containing all my nu i's. So let's write that down over here. So this guy is the vector of nu 1 star down till nu p star, right? And lambda star is a vector containing all my lambda i's. Lambda 1 star down to lambda m star. Okay, so now we've got that p star of 0, 0 is upper bounded by this quantity. So rewriting this, we get that p star of 0, 0 is actually this guy over here. So f0 of x plus lambda star transpose u plus nu star transpose v. Now we can get those two guys on the left hand side to get, actually this is a less than or equal, I'm sorry. So we get that f0 of x upper bounds p star 0, 0 minus lambda star transpose u minus nu star transpose v. Are we there yet? Well, yes. And why is that? It's because your cost is always an upper bound of what you see on the right hand side. Now for the particular case where x is x star, so pick x to be your x star, right? X star for the perturbed problem, of course. So x star for p. Then what can we say? For x star, f0 of x star is nothing other than p star of u and v, right? Because it's the optimal for the perturbed problem. So for that particular choice, we also have that p star of u, v is an upper bound of p star 0, 0 minus lambda star transpose u minus nu star transpose v. And the proof is done. So what we need to keep in mind from here is that the optimal value of the perturbed problem is an upper bound of that of the unperturbed problem minus two inner products, lambda star transpose u plus nu star transpose v. Okay? So what can we say about this? This is actually telling us something. It's not there for no reason. It's actually telling us something when we've got strong duality. It's telling us that when strong duality holds, we can say a lot of stuff, and in particular about the optimal Lagrange variables. So that is why I mentioned before that those optimal Lagrangian multipliers play a direct role on the optimal value of the problem. So if my lambda I star is large and we choose a ui to be negative, okay, so say that I've got only one m, so m is 1, that is I only have one inequality constraint. So I've got only one lambda star and only one ui, call it u, okay? So in that case, or if I just highlight on one of the m inequality constraints and I hold an argument over there saying, oh, let us imagine that I've got a lambda I star that is large and ui is negative. That is, we tighten the ith inequality constraint. Then guess what? The optimal value p star will largely increase. So the more lambda I increases, p star will increase. Okay, that's when my ui is negative. Now on the other hand, you can also increase p star by also choosing a positive vi and nu star to be large. So likewise, we need this guy to be positive. So one way of making this guy positive is by choosing a vi to be negative, right? So that this guy is positive and nu star to be large, okay? In that case, also p star is guaranteed to increase, right? So if I were to draw what's going on, if this is my u axis and say I've got only one inequality constraints and no equality constraints. So in that case, imagine this is my u, so my u equal to 0 will be here. This is u equal to 0. And right here, there's negative values of u. So my p star at 0 is just a constant, right? So my p star of 0 is constant. Then p star of 0 minus lambda star transpose u in this particular case will just be a straight line, right? So a straight line with direction lambda star. So for that, let's say this is my p star minus lambda transpose u, p star of 0 minus lambda star transpose u, right? This is my guy. And observe at u equal to 0, my p star of u should be equal, right? At u equal to 0, we see that this guy is this guy. So if I were to plot in red my p star of u right here, where the two curves coincide, right? P star of u and p star of 0 minus lambda star transpose u, they coincide. And as we said, as lambda increases largely, so given that u is positive and lambda is negative, we see that p star of u will diverge or will increase greatly with respect to p star of 0, and likewise from here, okay? So the larger u is, larger this guy is, with respect to lambda star, while minus lambda star is positive, then p star of u will increase greatly, okay? Now on the other hand, we've got another interpretation. So when lambda star is small and ui is positive, so this whole term is still negative, then the optimal value p star of u will not decrease too much, okay? So this whole thing is negative, but lambda I is small, so this whole thing will not decrease a lot. Makes sense, right? Because you're just pushing the right hand side lower by a small quantity. And likewise, when nu I star is small and positive, okay, because nu I could be positive or negative, and vi is positive, so again, all this quantity is negative, then p star of u and v will not decrease a lot. So we saw two cases, and for each case we also saw two subcases where p star of u is guaranteed to increase greatly or will not decrease too much. So it's guaranteed to increase greatly when my minus u is, positive, so you pick a u negative, and lambda star is large. Likewise, my minus v is positive, that is my v is negative, and my nu star is large. In that case, you're pushing the lower bound up. That is, you're pushing a lower bound of p star of u and v up. That is, you're guaranteed to increase p star of u and v, right? And on the other hand, when lambda star is small, then this guy will not change too much. Also, when nu star is small, given that minus vi or vi is positive, then this guy will not change a lot. So in the neighborhood, we're not decreasing p star of u and v too much, right? So this inequality gives us insights on the lower bound of the perturbed optimal value p star of u and v. But it does not give us any upper bound, right? For this reason, the results are not symmetric, right, with respect to loosening or tightening a constraint. For example, suppose that lambda I star is large and we loosen the ith constraint just a bit. That is, ui is positive. That is, this guy, the lower bound, is decreased. But this does not tell us anything about p star of u and v. Okay? So we do not have any symmetrical, this inequality does not give us anything what's going on in the other symmetric case. So we know that if lambda star is large and minus u is positive, that is, u is negative, that is, we tighten the ith constraint, we're pushing the lower bound up. So this guarantees that p star of u and v will increase. But what if lambda star is large and minus u is negative? That is, u is positive, that is, you're loosening. That is, your u is increasing positively. The lower bound will decrease, but that does not tell us anything about p star of u and v. Okay, now let's do some local sensitivity analysis. Okay, so over here we saw what happens when, u is large, small, lambda star is large, nothing locally. It's just that when you increase u unboundedly or when you increase lambda star, stuff like that. But nothing local to a certain point, let's say at 0, 0. That's what we're going to do right now. That's called local sensitivity. Did I write sensitivity wrong? No. Analysis. Okay. Now suppose that p star of u and v is differentiable at 0.00. So p star of u and v is differentiable at uv equals 0, 0, right? Then also assume that we've got strong duality. That is, p star of u and v is equal to d star of u and v, of course. Then what we can say is that the optimal dual variables, lambda star and nu star, have a certain relationship with the gradient of p star at uv equal to 0, 0. That are the following. So we can say that lambda I star is nothing other than minus the partial derivative of p star of u and v with respect to ui and evaluated at uv equal to 0, 0. Likewise, your nu I star is equal to minus partial derivative of p star u and v with respect to vi and evaluated at uv is 0. Okay, now you can see this from this figure. At u equal to 0, we can see that minus lambda star is the slope of p star near u is equal to 0, right? So over here it doesn't apply because the slope is as such, right? Neither does it apply here because the slope is as such, right? It only applies in the neighborhood of u equal to 0, so locally here. Over here, the slope is this line, right? So when, again, P star if U and V is differentiable at UV equal to 0 and strong duality holds, the optimal Lagrangian multipliers are exactly, as you can see here, the local sensitivities of the optimal value P star of U and V with respect to constraint perturbations that are UI and VI. Now, in contrast to what we had before, that is a lower bound on P star of U and V, which is not symmetrical. That is, we know what happens in some cases, not all cases. That is, when lambda star is large and minus u is positive, okay? That we know that, oh, we're pushing the lower bound up, so we're guaranteed to push with it P star of U and V up, right? However, in this case, no. We know what's going to go on both sides. Stuff are symmetrical. That is, tightening the ith inequality constraint a small amount, that is, taking ui small and negative, will increase P star approximately an amount of lambda I star multiplied by minus ui, right? And likewise, loosening the ith constraint a small amount, that is, taking ui to be small and positive, will decrease P star by an amount of lambda I star ui. Okay? Now, actually, if you're a bit lost over here, where did this come from? This actually has a proof. If you want us to prove it, let's do this. So, since P star of U and V is differentiable and strong duality holds, then for the perturbation, U is equal to TEI, where EI is the ith unit vector, that is, it is a vector of all zeros except 1 at its ith entry. Okay, so this 1 is at the ith entry. For this particular choice and for the choice of V equal to 0, that is, we're only perturbing in the ith inequality constraint a value of t. Okay, for this particular choice, what do we have? We can say that the limit as t approaches 0 of P star TEI 0 minus P star, that is evaluated at UV equal to 0, or P star, simply P star, the optimal value of C, divided by T. What is that? What is this term? This is a derivative term. It's actually the definition of the partial derivative at UI, right? This is the partial derivative with respect to UI and evaluated at UV equal to 0. Now, taking a look at the inequality we derived from the previous argument, right? If we have it here, then for t positive, we must have that this term right here is greater than minus lambda I star. And why is that? Well, simply just, get this guy on the left hand side, right? V is 0. You're left with minus lambda star u. But u is just TEI, right? So lambda star u in that particular case would just be T lambda I star, or T lambda I star. Okay? So this to this is simply just U is EI, and V is 0. That's it. We're just applying the inequality for this particular choice. Okay? So for t positive, that's what we have. And now letting t go to 0, as t goes to 0, we can use the partial derivative definition, right? So this guy, we're going to use it here, and what we get is partial derivative of p star at 0 is greater than the right hand side, that is minus lambda I star, right? But this is when t is positive, so when t approaches 0 from the positive side. Now what happens if t is negative? So for negative t, we actually have the same inequality, but this guy is flipped. So you can actually prove that you have this, okay? This is for t negative. Now taking the limit, when t approaches 0 from the negative side, you get the same thing over here. You get the same inequality but flipped. Now combining both results, combining this guy and this guy, what we get is that the partial derivative of p star with respect to ui evaluated at 0 is minus lambda I star. And the same method could be used to prove nu I star is the derivative with respect to vi. It's the negative of the partial derivative with respect to vi and evaluated at 0. Okay, so now what can we say over here? This actually gives us a measure of how active a constraint is at the optimal point x star. It tells us that if my fi of x star is negative, then the constraint is simply inactive, which means that the constraint is inactive. It follows that the constraint can be tightened or loosened an amount without affecting the optimal value. Now, we know that by complementary slackness, the associated optimal Lagrangian multiplier must be 0. But now, let's say that, we have that fi of x star is 0. That is, the ith constraint is active at the optimal point x star. The ith optimal Lagrangian multiplier tells us how active this constraint is. If lambda I star is small, it means that the constraint can be loosened or tightened a bit without much affecting the optimal value. On the other hand, if lambda I star is large, it means that if the constraint is loosened or tightened a bit, if it's changed a bit, the effect on the optimal value would be great, which is what we expect, right? So if lambda I star is large, it's telling you any short perturbation, any small perturbation will affect the optimal value a lot. So it's actually also highlighting on the constraints, telling you, okay, so if my lambda I star is small, then tightening or loosening, the constraint just a bit will not affect x star, which makes sense, okay? Whereas if it's large, it tells you that, any small perturbation of ui will highly affect the optimal point x star. Now in economics and finance, we can also give a simple geometric interpretation of what we have over here. We consider, for simplicity, a convex problem with no equality constraints. That is, we don't have nu I star just for the sake of argument. and also assume that Slatter's condition holds. Now the variable x of the problem determines how a firm operates. And the objective f0 of x, right here, is the cost. That is, minus f0 of x is the profit. So you're minimizing the cost, or equivalently, you're maximizing profit. Each constraint fi of x represents a limit on some, resource, such as, maybe warehouse space or labor, or maybe wood, or it depends on what you have going on, right? Now, in that case, if minus f0 of x is profit, then minus p star of u tells us how much more or less profit could be made if each resource were made available to the firm. So we don't have exactly how much, let's say warehouse space exactly. We don't know exactly the warehouse space, right? We only have an idea, plus or minus a certain nominal value. So in that case, you will know from lambda I star which constraints are, could be tightened or relaxed, right? Without much affecting the profit, P star minus P star of u, and which ones do. So that said, if P star if u is differentiable near u equal to 0, then we have that lambda I star is minus that partial derivative at 0. In other words, lambda I star will tell us approximately how much more profit the firm could make for a small increase in availability of resource I. Okay? You can also see that lambda I star acts as a sort of equilibrium price for resource I, if it were possible for the firm to buy or sell it. Now, say for example that the firm can buy or sell resource I at a price that is less than lambda I star. In this case, it would certainly buy some of the resource, right? Which would allow it to operate in a way that increases its profit more than the cost of buying the resource. On the other hand, if the price exceeds lambda I star, the firm would sell some of its allocation of resource I and obtain a net gain, since its income from selling some of the resource would be larger than its drop in profit due to the reduction in availability of this particular resource. Okay? So that's all I have to say. So we just gave a shadow price interpretation. So that's it for this lecture. I hope you enjoyed it. I hope you found it beneficial. We talked about perturbation and sensitivity analysis. That is, we introduced a perturbed problem of the classical optimization problem. We saw what it means to tighten and relax constraints, inequality constraints. We also defined the optimal value of the perturbed problem, that is a function of u and v. We gave an inequality that is global, in a sense that we did not assume convexity of the problem, but this illustration is for a convex problem. But this inequality could be applied for any type of optimization problem given strong duality. You can say this, but it turns out that for this inequality we don't have symmetry. That is, we know what happens, let's say, for the case where lambda star is large and minus u is positive, but that is, we're pushing the lower bound upwards. So p star moves upwards. But we don't know what happens when lambda star is large and minus u is negative. Okay, that is, u is positive and you're relaxing the constraint. In that case, the lower bound is pushed downwards, and we don't know how p star of u and v will react to this type of perturbation. On the other hand, we gave a local sensitivity analysis discussion, which is, unlike the global inequality, it is symmetrical. That is, we know what happens on the left and right of a certain point, right? We gave an interpretation in terms of economics, that is the shadow price interpretation. If you have a certain industry going on, producing income, you're trying to maximize profit. We saw that an interpretation of lambda I star has implications on resource I. That is, if it were possible for a certain industry to buy or sell resource I, then lambda I star would act as an equilibrium price for resource I. That is, say that the firm or the industry can buy or sell resource I at a price that is less than lambda I star. In this case, it would certainly buy some of the resource, because if it's cheap, then yeah, there is a threshold, call it lambda I star, which is the equilibrium price, in which if the price of that resource is less than this amount, the firm would definitely go and buy this resource. On the other hand, if the price exceeds lambda I star, then the firm would sell some of its allocation of resource I and obtain a net gain, since its income from selling some of the resource will turn out to be larger than its drop in profit. So that's one interpretation in economics that is called the shadow price interpretation. Thanks for watching. I hope you found this lecture beneficial. If you did, please leave a like on the video, subscribe to the channel. Let me know what you think down in the comment section below. And if you can go ahead and contribute to my Patreon account. Thanks for watching, and I'll see you in future lectures.